Okay, I'm going to talk about just how to graph this really quick, and then we'll kind of look at one of these problems down at the bottom. So we left off talking about h of x and the transformations that can occur on a quadratic function. So again, if we were to identify these based off of what we know with absolute value functions, so remember absolute value, if it was h of x and it was instead -2 absolute value of x plus 3, we could identify these transformations. This one is moving up 3, right? It shifts that vertex up 3. This out front is going to stretch vertically by 2, so that slope's changing. And then this right here, right, reflected it. I know you can't even read that, over the x-axis. This same thing occurs with a quadratic function. So this plus 3 right here, because there's no middle term, now notice there's no middle term, if we add 3, we are moving the graph up 3, or the vertex up 3, right? This negative out front, same exact thing, it's going to reflect it. This 2 is going to stretch it. Now, with an absolute value function, 2 became the slope. 2 is going to multiply by the square value, so it's not actually going to become the slope. So 2 ways you can do this. One, you can plug it into your calculator. So I'm going to show you, if you have your calculator, you can go ahead and open it up. And I say open it up, I guess turn it on. And you could go to y equals, and you could plug in -2x squared plus 3. And we could graph that, and we could see that it's going to, right, reflect it. It's going to move it up 3. If I want to plot some of the points, I would go second graph. That takes me to this table. And I could plot these points that fit on the table on the graph. So -2, -5 would be 1 point. -1, 1. 0, 3, 1, 1. So we can just plot those on our graph over here. So -2, -5 fits on the graph. -1, +1. 0, 3, these are all from that table. 1, 1, and 2, -5. And the rest of them kind of go off the graph, so that's as many as I'm going to do. And then I can draw my U shape as best I can here, using making sure it looks like a U instead of a V. Again, you can do that without using the calculator if you like to. Again, you just start with the shifts. So normally we sit here, but this one's shifted up 3 and reflected over, and it's going to stretch by 2. So if you're 1 unit away from the vertex, generally a quadratic function goes up 1 because it's 1 squared. If you're 2 units away, it usually goes up 4 because 2 squared is 4. And 3 squared is 9. So you're looking at these different ones. Oh, I don't think I went very far enough. You're looking at that one, but this has been stretched. So notice it's just doubled. That's up 2. Instead of 4, it's up 8. So it's been stretched to be steeper. So you can graph it that way too. And then just the comparison is just stating the transformations. So how is this one different than that red parent function that's on there? Well, this one's been reflected over the x-axis, so it's now pointing down. It's been shifted up 3, or translated up 3, and it also has been stretched vertically by 2. So those are all the 3 transformations that are taking place. From there, once we have a function written, we can actually change the function. So for example, if I wanted to create a new function called g of x, and we wanted to just take h of x, right, and subtract 5, or in other words, shift it down 5, we can do that. We just take g of x, and we take h of x. Now, h of x was -2x squared plus 3, right? We could put it in like brackets if we wanted, just to remember that that's the function, and then we're subtracting 5 on that. Notice when we create our new function g of x, we just have -2x squared. The 3 can combine with the -5, giving us a -2. And again, if I did that off of the graph, here's that original h of x. This one is going to shift it down 5. So if I go down 1, 2, 3, 4, 5, notice my function would be down here. And that's exactly where this one is now. It's down 2. So it's going to look the same. The very last thing on here, what is the difference between finding, identifying the x-intercepts, and finding or solving for the zeros? They're the same thing. We generally talk about find the x-intercepts when we're looking at a graph because it just makes more sense. That's what we call them. They're identified on the x-axis. But when it says solving for the zeros, that's the same idea. So if you're given a function, say we're given f of x, right, is equal to 4x squared minus 9. If we're talking about transformations, this one's been shifted down 9, right? This has been stretched vertically by 4. But if we wanted to solve that, then we say, well, when is the function equal to 0? And again, this is just like your last homeworks. So you take this and you look to see if it's factorable. Is there a greatest common factor? In this case, no. So I am going to pull this apart as a difference of squares. So this would be 2x minus 3 and 2x plus 3. So my solutions there, if I'm finding zeros from that first piece, right, this piece right here, would be x is equal to 3 halves, or 1.5. So my two zeros would be x is equal to 3 halves, and the other one, x is equal to negative 3 halves. So if I were to go ahead and graph that function, I should be able to see that its x-intercepts would occur at 1.5 and negative 1.5.